We continue with the topic linear span. So today's theorem is if S and W are non-empty subsets of vector space VF, then number 1, if S is a subset of W implies linear span of S, linear span of W. Second, S is a subspace of V if and only if Ls equal to S. Third, linear span of S is equal to linear span of S. And fourth, linear span of S union W is linear span of S plus linear span of W. So let us make it as write it as capital S. So what is our theorem? If S and W are non-empty subsets of vector space VF, then number 1, if S is a subset of W, this implies linear span of S is contained in linear span of W. So we write down the proof of the first one. Let S subset of W, S be a subset of W. Then for any U belongs to linear span of S, this implies U can be written as a linear combination of elements of S. That is, U can be written as a linear combination of AI, UI, where AI are the members of field and UI are the members of S, and I varies from 1 to N. This implies U belongs to LW, that is linear span of W, since UI belongs to W for I equal to 1 to N. As you know that UI belongs to S, S is a subset of W, therefore each UI belongs to W. This implies U belongs to LS, or you can say that or U belongs to LS implies, now U belongs to LS implies U belongs to linear span of W. This means linear span of S is a subset of linear span of W. Hence, we have proved that if S is a subset of W, this implies linear span of S is subset of linear span of W. Second, let S be a subspace of V. To prove that linear span of S is equal to S, we know that from the definition of linear span, we know that S is subset of linear span of S. Then for any U belongs to linear span of S implies U can be written as a linear combination of elements of S. That is, U can be written as U is a summation AIUI where I varies from 1 to n, and you know that AIs are the member of the field and UI belongs to S for I is 1 to n. Since AI belongs to field and UI belongs to S, and S is a subspace of V. Therefore, AIUI belongs to S for I, each I vary from 1 to n. This implies, because A1 U1, A2 U2, all AN UN belongs to S, so their linear combination I vary from 1 to n, AIUI belongs to S from the definition of subspace, and this means U belongs to S. Since now what we have, U belongs to LS implies U belongs to S. Now what we have, U belongs to linear span of S implies U belongs to S, and this means linear span of S is a subset of S. Since S is a subset of LS and LS is a subset of S, hence linear span of S is equal to S. Conversely, let S be a non-empty subset of vector space VF such that linear span of S is equal to S. We know that because we already proved that linear span of S is a subspace of V, is a subspace of V, hence S is a subspace of V because LS is equal to S, and since LS is a subspace of V, hence S is a subspace of V. Now the third part says that linear span of LS is equal to LS. So it follows from the second The proof of third directly follows from the proof of second. That is, the result directly follows from to as linear span of S is a subspace of V. So linear span of LS is equal to linear span of S. That is, in second part we replace S by because we know that linear span of S is S whenever S is a subspace of V. Since LS is a subspace of V, so we replace S by LS. So by following this or by following second, the result of 3 follows directly. Next is the fourth one. Fourth one says that ki linear span of S union W is equal to linear span of S plus linear span of W. So this we will left as an exercise. You can try it. So fourth one left as an exercise. You may try it by your own. If you feel any problem, then let me know. I will tell you the solution of this. So next we have very important example. The example says every plane through the origin in R cube is a subspace of R cube. So what is solution? Let us see its solution. Let omega be a plane through the origin in R cube with directions vector u1 and u2. So we can write omega as a span of u1, u2. Since 0 can be written as 0 u1 plus 0 u2. The 0 vector, or you may write in language, the 0 vector belongs to omega. Now let any two vector, say v and w, belongs to omega such that v is a1 u1 plus a2 u2, and W is B1 U1 plus B2 U2. Then the sum of these two vectors V plus W is A1 U1 plus A2 U2 plus B1 U1 plus B2 U2, and it gives you A1 U1 plus B1 U1 plus A2 U2 plus B2 U2. By using the commutativity and the associativity property, so we get A1 plus B1 U1 plus A2 plus B2 U2. Since V plus W is again a linear combination of U1 and U2, so this vector V plus W is a linear combination of U1 and U2, and so is in omega. Now let C be any scalar. C be any scalar quantity, then CV means C A1 U1 A2 U2 gives us C A1 U1 plus C A2 U2. You may write as C A1 U1 plus C A2 U2. Again CV, this shows that CV can be expressed as a linear combination U1 and U2, and so is in omega. Now we have shown that omega satisfies all the three properties of subspace, hence it is a subspace. It is a subspace of R cube. Here you may observe the role of vectors U1 and U2. U1 and U2 are used generating the subspace of R cube. We can generalize this for arbitrary set of vectors in Rn to obtain different subspaces of Rn. Thus, generalization of the result given in this example give rise to the following theorem. That is, generalize of the above example give us the following theorem. Let U1, U2, Un be vector in vector space R. Let U1, U2, UN be vectors in vector space R. Then the span of U1, U2, UN is a subspace of R. Let us write down its proof. Let B is a span of U1, U2, UN. The zero vector 0 is in B, since 0 can be written as 0 U1 plus 0 U2 plus 0 UN. Now let V and W are the two vectors in B such that V is a linear combination of elements of span of V U1 U2 UN, that is V is A1 U1 A2 U2 plus AN UN, and W is B1 U1 B2 U2 plus B2 U BN UN. BN UN. So their linear combination, then the linear sum V plus W is A1 U1 A2 U2 plus AN UN plus B1 U1 B2 U2 plus BN UN. As we have done in the previous example, similarly by rearranging and applying commutative and the distributive, commutative and the associative laws, we may write down it as A1 B1 U1 A2 plus B2 U2 and AN plus BN UN. Since V plus W is a linear combination U1 U2 UN, so is in B, that is V plus W being a linear combination U1 U2 UN, V plus W belongs to B. Now let C be a scalar number, that is C belongs to field. Then CV gives us C A1 U1 A2 U2 plus AN UN. Thus gives us C A1 U1 C A2 U2 plus C AN UN. Again using the associative property, C A1 U1 C A2 U2 plus C AN UN. This shows that CV this shows that CV can be expressed as a linear combination of U1, U2, UN, and so is in B. Thus, in this way, we have shown that B satisfies all the three properties of subspace. Hence, it is a subspace of R. You can see very well in the proof of this theorem, which is generalization of example. The proof is written in the similar pattern as we have written the solution of this example. So, you should be always very careful what we have done in the solution and what we have written in the exam in the proof of the theorem. The pattern is similar. So, if you practice carefully the example, you may able to write down the proof of the theorem. The example is only for the two vectors, that is for the plane, and here theorem is about the space which is spanned by the any number of vectors u1, u2, un. You may also try this example. You may also try this example. What this example says that every line through the origin in R cube is a subspace of R cube. So here, in case of line, think about line is a span of how many vectors, and then write down the proof based on the above theorem. So, we may stop here.